Hello everyone, welcome to the BYJU'S Exam Prep. I am Ajay Gupta and I welcome all of you in my class of 51 expected questions of electrical machine. In last week we started this series and we are doing the complete revision of electrical machine while doing the problem of different machines. We already completed the transformer, induction machine and the DC motor. And today I will discuss the synchronous machine and we will try to cover the complete concept of synchronous machine while doing these problems. So welcome everybody, and I request all of you please share this link to other students so that they may also connect it with us. So the modus operandi of this class is that in today's class I will cover the 15 problems of synchronous machine. I will give you the 4-minute time to solve this problem. First you have to do by your own, and after that I will discuss each and every problem while discussing the complete detailed solution as well as the concept behind that problem. So good morning everybody. Good evening everybody. So let us start with the synchronous machine. So this is about me. I am Ajay Gupta. I have done my BTech from NIT Jaipur and I got the single digit rank both in ESC exam as well as the GATE exam. I take the electrical engineering core subject like machine, power electronics, power system, and I also take the control system and the network theory. So this is the first question of my class. It is from the alternator. A 3-phase 12-pole star-connected alternator has 180 slots. The total number of slots in the alternator is 180 slots with 10 conductor in each slot. Not conduction, it is basically conductor in each slot. The conductor of each phase connected in series. The coil span means the coil pitch is 144 degree electrical. Determine the line value of induced EMF if machine is running at 600 rpm speed and the flux per pole is 0.06 Weber distributed sinusoidally over the pole. So the 4 option is given. I will give you the 4-minute time to solve this problem. So I am taking the stopwatch and your time starts now. Good afternoon Chakravarti. Good afternoon Vaibhav. Three-phase 12-pole star-connected alternator. It has total number of 180 slot with 10 conductor per slot. This is the conductor per slot, and the conductor of each phase are connected in the series. The coil span, that means the coil pitch is 144 degree electrical. Determine the line value of induced EMF. The line value, the line induced EMF you have to tell if the machine is running at 600 rpm and the flux per pole is 0.06 Weber and the flux is distributed sinusoidally over the pole. Induced line EMF. Good afternoon Shivanke. I am just giving a hint. First find out the induced EMF per phase and from that then you find out the line EMF. Use the formula of induced EMF per phase first, then by using that per phase quantity then find out the value of line EMF. In this alternator, we are using the short pitch winding as well as distributed winding. Okay, I will tell the name of Telegram channel. My Telegram channel is Ajay Gupta _ JPR. सर आप NWE हो. NWE means still you have 1 minute and 5 seconds. क्वेश्चन ब्लर हो रहा है बट मेरे को तो एकदम करेक्ट दिख रहा है यहाँ पर. आई एम ऑल्सो वॉचिंग ऑन माई लैपटॉप. Last 42 seconds remain. Still I have not get any answer from any student. It's a very simple question, only based on the formula. Hello Ankit, how are you? As per the Ayan, C is the correct option. That means the 4350. You have to find out the induced light EMF, not the per phase EMF. Light EMF. Good evening, Nisi. As per the above, C is the correct option. And your time is up. Now let me do this question for you. See, always read the question 2 times and highlight the keyword. It is a 3-phase star connected alternator. The total number of slot in the alternator is 180 slot, and in each slot we have a 10 conductor. Each phase winding is connected in the series. The coil span means the coil pitch. The coil pitch is 144 electrical degree. Determine the value of in line EMF, not the phase EMF, the line induced EMF. If the machine is running at 600 RPM speed and the flux per pole is 0.06 Weber and it is distributed sinusoidally over the pole, that means the no harmonics is existing here. Okay, so see, we know that the per phase formula of induced EMF, it is under root 2 pi f. Under root 2 pi means 4.44 f into n phi multiplied by kW. Induced EMF per phase means we will use here the total number of turn per phase. Under root 2 pi f nph phi into kW. So first we have to, the kW is the winding factor, and the winding factor is the multiplication of pitch factor as well as distribution factor. So first we will find out the value of pitch factor and the distributed factor. So see here, the coil pitch is given. The coil pitch is 144 degree electrical. Coil span and coil pitch is the same thing. So coil pitch, it is always given in the electrical degree. It is 144 degree electrical. If you know the coil pitch, we know that the pole pitch is always 180 degree electrical. Pole pitch means the distance between two adjacent pole is called the pole pitch, and the pole pitch is always 180 degree in term of electrical. It is the electrical. So the difference between pole pitch and the coil pitch is called the chorded angle. So the short pitch angle or the chorded angle. First I will find out the short pitch angle or chorded angle. It is also called the chorded angle. Short pitch angle is the pole pitch minus coil pitch. If I subtract coil pitch from the pole pitch, I will get the short pitch angle. So 180 degree minus 144. You will get the 36 degree electrical. It is called the chorded angle. It is epsilon is equivalent to 36 degree electrical angle. So what is the pitch factor? The pitch factor is cos epsilon by 2. Epsilon means the short pitch angle. So cos 36 by 2, that means the cos 18 degree is the pitch factor. If I calculate, I will get the value 0.95. So the pitch factor is equivalent to 0.95. Now I will find out the distribution factor so that we will be able to find out the value of winding factor. So what is the formula of distribution factor? Formula to calculate distribution factor is sin q gamma by 2 divided by q sin gamma by 2. Now what is these all quantity? What is the q? Q is the phase spread. It is called the slot per pole per phase. Slot per pole per phase. It is called the phase spread. So the total number of slot in alternator is equivalent to 180 degree. It is 180 degree. Total number of pole and total number of phase. It is a 3-phase alternator and the total number of pole is 12. So 3 into 12 into 3. So phase spread we are getting is 5. Phase spread means there are 5 slots which belongs to same pole and the same phase. Now slot angle gamma. The slot angle gamma is 180 degree divided by slot per pole. This is the formula to find out the slot angle. So 180 degree divided by slot per pole. We know total number of slot was 180 and total pole was 12. So the slot angle is equivalent to 12 degree. If I put the value of q and gamma in this formula, I can get the value of kd. So kd is sin q gamma by 2. Q is 5, gamma is 12 divided by 2. Q sin gamma by 2. Q is 5 sin 12 by 2. If I calculate, I will get the value 0.957. So in this way, we have find out the value of Kp and the Kd. In this formula, now we know the value of Kw. Phi is already given. We have to find out the value of frequency, the frequency of induced EMF and the number of turn per phase. So how to find out the frequency of induced EMF? F is the frequency of induced EMF. So frequency of induced EMF what is the formula of induced EMF? It is depend upon the total number of pole speed divided by 120. The total pole is 12 pole. Alternator was running at the speed of 600 rpm divided by 120. So the frequency of induced EMF is 60 Hz, not the 50 Hz. It is the 60 Hz. Remember this thing. It is the Hz. Now we have to find out the total number of turn per phase. How to find out the total number of per phase? To find out the total number of per phase, first I will find out the total number of turn and it will divide by the total number of phase. Clear? First I will going to find out the total number of turn in complete alternator and I will divide this with the total number of phase. So see what is given. The alternator has the total 180 slot and each slot contain 10 conductor. So total number of conductor in alternator. Alternator having a slot 180 and each slot is having a conductor of 10. So we have a 18 number of conductor, 1800 number of conductors in the alternator. Now we know 1 turn is equivalent to 2 conductor. We know 1 turn, in a single turn we have always 2 conductor. See, this is my winding. This is a single turn. In single turn we have 2 conductor, one this side and one this side. So what will be the total number of turn? If I divide total number of conductor by 2, I will get the total number of turn in the machine. So it has 900 number of turn. Total number of turn is the 900. But in this formula we have to find out the total number of turn per phase, because we are going to find out the induced EMF per phase. So let us find out the total number of turn per phase. If the machine has 900 total turn and the total phase is the 3, so NPH is become 300. Now just put the value of everything in the formula. So induced EMF per phase is under root 2 pi NPH F into flux. Under root 2 into pi, NPH is 300 multiplied by winding factor. F is the 60 Hz. F phi here is the flux per pole, and the flux per pole is given, it is 0.06. Winding factor is multiplication of pitch factor and the distribution factor. Pitch factor is the 0.95 and distribution factor is 0.957. If you calculate, what you will do, you will find it is the 4350 volt. It is not the line induced EMF, it is the induced EMF per phase. Remember, it is not the line induced EMF, it is the induced EMF per phase. Now see, it is a star connected alternator. So in star connected alternator, the line voltage is root 3 times of the phase voltage in star connection. Do not commit this type of silly mistake. That is why always read question 2 times before giving the answer, because everybody is given the per phase induced EMF, but in this question they was asking about the line induced EMF. So it is the root 3 times of the 4350. If you calculate, you will get the 7350 volt. Is it clear? That is, I always say, read the question 2 times before giving the answer. If you read the question 2 times, you always avoid the silly mistake, because in this question they was not asking about the per phase voltage, it was asking about the line induced EMF. And since it is the star connected, because the most of the alternator is connected in the star, so the line voltage will be root 3 times of the per phase voltage. Is it clear? Should I move to the next question? Yeah, definitely, Sai. You will get these type of questions, lectures for GATE in 2023 too. Okay, so here we go with the second question. See, I always see most of the students just remember this formula to find out the induced EMF per phase. Suppose if in this exam somebody asks you the induced EMF per conductor or induced EMF in a coil, so how to perform these type of question, because you have to learn the complete concept, where we have to use the pitch factor, where we have to use the distribution factor. We cannot use pitch factor and distribution factor every times. So suppose now I will show you how to find out the induced EMF in a conductor and induced EMF in a coil. So this is my second question. A 10 pole 50 Hz 600 RPM alternator has a flux density distribution of B equivalent to 1 sin theta. Sin theta means it is a space angle. That means the flux density is sinusoidally distributed in the air gap. The alternator has 180 slot. This is the total number of slot with 2 layer and 3 turn coil having a span of 15 slot if armature diameter is 1.2 meter and the core length is 0.4 meter, then the RMS value of induced EMF in a single conductor. See, here you have to find out the RMS value of induced EMF in a single conductor, not induced EMF per phase or not induced EMF in a line voltage. So find out the induced EMF in a single conductor. I am giving you the 4-minute time to solve this question. Now today you will learn how to find out the induced EMF in single conductor, how to find out the induced EMF in a coil, and how to find out the induced EMF per phase in a winding. The winding has a number of coil and a single coil has a number of conductor. So it is again questions belong to alternator, a 10 pole 50 Hz 600 RPM alternator. The flux density is distributed is sinusoidally 1 sin theta. The alternator has total 180 slot wound with the 2-layer 3-turn coil. The coil span is equivalent to the 15 slot. Here the coil span is not giving in term of electrical degree. Here it is giving in term of slot. If alternator diameter is given and the core length is given, the RMS value of induced EMF per conductor will be. From the flux density, find out the flux. Two minutes 25 seconds left. Yes, true, Ismail. What is your doubt? Sit with the pen, pencil, calculator and the copy with this class and try to solve all these questions by your own. If you are not able to solve this question, do not demotivate it. Just try to learn the new concept before the gate examination. Yes, still you have 1 minute. Just in a single conductor, you have to find out the induced EMF. Only in a single conductor. Not induced EMF per phase or not induced EMF between the two line terminal. B 10.65. As per the ion, 10.65 is the correct option. What about the others? What is the induced EMF per conductor? The formula of induced EMF per conductor is applicable everywhere, whether it is a synchronous generator or it is a DC generator. The formula is always remains same, because this formula belongs to the rotational EMF, how much the rotational EMF is inducing in a single conductor. Last 2 seconds. Oh, and your time is up. Okay, let me attempt this question for you. See, first tell me what is the formula to find out the induced EMF in single conductor. Which formula you use to find out the induced EMF in a single conductor? Because this formula is applicable to find out the induced EMF per phase. So you cannot use this formula, because in the per phase we can use a number of winding in a number of winding we can have a large number of coil, and each coil has a large number of conductor. So what formula you use to find out the induced EMF in single conductor? Yes. So the formula that we use to find out the induced EMF in single conductor is induced EMF in a conductor. This is a general formula. It is equivalent to P small n multiplied by phi. It is applicable for synchronous machine as well as DC machine. This is the general formula to find out the induced EMF in a single conductor. Here phi is the flux per pole. We use here the flux per pole. And P is the total number of pole, and n is the speed in rotation per second. Small n means rotation per second. If I use capital N, that will represent the rotation per minute. So how to find out the flux per pole? Because the flux per pole is not given. In place of flux per pole, the flux density waveform is given. It is the B equivalent to 1 sin theta. That means if I draw the flux density with respect to space angle, if you draw the flux density with respect to space angle, it is a sinusoidally distributed with respect to theta. This is my flux density with respect to theta. And the maximum value of flux density is equivalent to 1. It is the Bm. So Bm is equivalent to 1. It is given Bm. So first I will find out the average value of flux density. So how to find out the average value of flux density? Because to find out the flux per pole, I need the average value of flux density. For a sinusoidal waveform, suppose if it were the voltage waveform and the magnitude of voltage is the maximum voltage of voltage is the Vm, then what is the average voltage here? 2 Vm upon pi. So similarly here it would be the 2 Bm upon pi. This is the average flux density of a sinusoidal quantity. Okay. So what is the Bm? Bm is equivalent to 1. Maximum value of flux density is equivalent to 1 divided by pi. So its average flux density is 0.637. Is it clear? This is the average value of flux density. To find out the flux per pole, I multiply by average value of flux density with the area of per pole. So to find out the value of flux per pole, flux means that it is a flux per pole. So if you multiply by average value of flux density with the area per pole, you will get the flux per pole. So how to find out the area per pole? It is a cylindrical surface area. The length is given and the diameter is given. So in a length and diameter is given, what is the surface area of a cylindrical surface? Surface area is 2 pi RL or pi dl. Pi dl or 2 pi RL divided by P. So D is given, L is given. Flux density we just find out 0.637. Pi. What is the bore diameter? It is 1.2 meter and length is 0.4 meter. So 1.2 into 0.4 divide by total number of pole. Total number of pole is 10. So by using this formula, you can find out the average value of flux per pole. It would come 0.096 Weber. Is it clear? This is by flux per pole. To find out the flux per pole, first I find the average value of flux density and multiply it by area into area divided by pole. So this is the P and phi. Now at which speed is it rotating? It is the 600 RPM rotating. N is the 600 RPM speed. RPM is the rotation per minute. So what is the small n? Rotation per second. It would be 600 divided by 60 because 1 minute has the 60 second. It has become rotation per second. So small n is 100 rotation per second. Is it clear? Now tell me, if you are going to find out the induced EMF in a single conductor, whether you would multiply it by pitch factor or the distribution factor or not. If you have to find out the induced EMF only in a single conductor, whether you will take the pitch factor and the distribution factor into account or not. Because if you are going to find out the induced EMF in a single conductor, it is nothing to do with the pitch factor and the distribution factor. Because we have to just find out the induced EMF in a single conductor. Single conductor does not have pitch factor or distribution factor. So don't use pitch factor and the distribution factor. Just use P and phi to find out the induced EMF. See, since here we are using the average value of flux density, so this formula represents the average value of induced EMF. P n into phi. Total number of pole was 10 pole. Speed in rotation second we just find out. It is 100. And average value of flux density is 0.096. If you calculate, you will get the 9.6 volt. This is the average value of induced EMF. But see, when the flux is sinusoidally distributed in the air gap, the induced EMF that will develop in the single conductor, it will be sinusoidal with respect to time. The induced EMF would also be the sinusoidal with respect to time because the flux density is sinusoidally distributed. So we have just find out the average value of induced EMF. So what will be the RMS value of induced EMF? If you know the average quantity, how to find out the RMS quantity? Average quantity multiply by form factor, and the form factor of a sinusoidal quantity is 1.11. So multiply it by 1.11. You will get 10.65 volt. So do not use any pitch factor or any distribution factor if the question asks to find out the induced EMF in a single conductor, because the single conductor does not have any pitch factor, it does not have any distribution factor. Clear? And first find out the average value of induced EMF, and from the average value of induced EMF then find out the RMS value of induced EMF, because the RMS value is the average value multiplied by form factor, and the form factor of sinusoidal quantity is 1.11. Is it clear? I will use same data in the three questions just to find out the difference between induced EMF in a single conductor, induced EMF in a coil, and the induced EMF in a winding. Clear? So see, I am moving to the question number 3. It has all the same data that we used in the previous question. A 10 pole, 50 Hz, 600 RPM alternator has the flux density distribution of 1 sin theta. The alternator has 180 slot wound with 2-layer 3-turn coil, everything same, and the coil span is also given, that is the 15 slot. Armature diameter and core length was given, but here you have to find out the RMS value of induced EMF in a coil, not per phase. In previous question we found the induced EMF in a conductor, and here you have to find out the induced EMF in a coil. So again I am giving you the 4-minute time to solve this question, and your time starts now. Just try to find out the difference between induced EMF in a coil, induced EMF in a conductor, induced EMF in a winding. So by using 3 questions using the same data, I will show you what is the difference between all these quantities. You can use the answer of the previous question to find out the induced EMF in a coil. The data is same as we used in the previous question. But in this problem, you have to find out the induced EMF in single coil. The coil may have large number of turn, and each turn has the 2 conductor. C 61.72. As per Nisi, Ayan and Neeraj Kumar Maurya, the answer is C. As per these guys. $61.43. Sorry, your stopwatch stopped. Okay, the guys who have solved this question, just tell me, to find out the induced EMF in a coil, should we use the pitch factor or distribution factor into account? Should we have to use the pitch factor or distribution factor into account? Or we do not use any pitch factor or distribution factor? Nisi Tiwari is saying yes. Prakash Chandra is saying yes. As per Nisi Tiwari, we use only KP. We will not use KD. Always remember how the winding is formed. The winding may have the large number of conductor. From the conductor, the turn is formed. From the turn, the coil is formed. From the coil, the winding is formed. And from the winding, we have the total number of winding in per phase. I think I have given enough time to solve this question because in between the stopwatch was stopped. So I'm just trying to solve this. See. First tell me about this. This is a single conductor. Is it clear? And single turn has the 2 conductor. this is my single turn. Turn is made from the two conductor. This is become a turn. Turn has two conductor. This is a one conductor and this is another conductor. Suppose if in a coil we use large number of turn. Suppose instead of using 1 turn coil, it may have 3 turn coil or 4 turn coil. So see, if I take the 2 turn coil, now this is a 2 turn coil. Is it clear? This has become 2 turn coil. This is a coil which have the 2 turn. 2 turn means it is a 1 turn and this is a another turn. So in every coil we have a 2 side. This is one side, it is called the coil side. And this is the another coil side. Every coil has a 2 coil side. One is placed on under the one pole, under the influence of one pole, and second is placed under the influence of another pole. So one coil has a 2 coil side. 2 coil side. In a winding may have a large number of coil. The winding may have 2 coil, winding may have the 3 coil. So here we have to find out the total number of induced EMF only in a single coil. So suppose it is a 3 turn coil. In a 3 turn coil, how many conductor it has? Because the one turn has the 2 conductor. I told you 1 and 1. One turn has the 2 conductor. So it has a 6 3 turn coil. So in this coil, it is a 6 turn coil. Sorry, 3 turn coil. Since we know the one turn has the 2 conductor, so the 3 turn would have 6 conductor. Clear? It is a 6 conductor. And in the earlier question, we just find out the induced EMF in a single conductor. If you know the induced EMF in a single conductor and it has the 6 conductor, so multiply it by 6, you will get the induced EMF in a coil. So induced EMF in a coil it is induced EMF in a conductor and we know in this coil we have a 6 conductor. So multiply it by 6. You can get the induced EMF in a coil. But this would give the right answer if my coil is a full pitch coil. What is the full pitch? The distance between 2 coil side is called the coil pitch. This is called the coil pitch. If the coil pitch is equivalent to the full pitch, that means it is a full pitch winding. But if coil pitch is less than the pole pitch, then it is called the short pitch winding. And we know if we use the short pitch winding, the induced EMF is reduced by the pitch factor. So here we are using the short pitch winding because the coil span is having only 15 number of slot, which is less than the pole pitch. So I have to multiply it by a pitch factor. So to find out the induced EMF in a coil, we have to take the induced EMF into the account. But we do not use the distribution factor here because it has nothing to do with the distribution. Because we have in a coil we have only 2 coil side and 2 coil side would be placed in the 2 slot. Clear? So see how to find the pitch factor. To find out the pitch factor, it is a difference. First we have to find out the chorded angle. It is equivalent to cos epsilon by 2. And chorded angle is the pole pitch minus coil pitch. What is the pole pitch? In terms of electrical degree, the pole pitch is always 180 degree electrical. But in terms of number of slot, because the coil pitch is given in number of slot. So in terms of number of slot, what will be the pole pitch? In term of number of slot, we know the pole pitch is the slot divided by total number of pole. So the alternator has 180 slot and the total pole is 10. 180 divided by 10. The pole pitch is equivalent to 18 slot. It is equivalent to 18 slot, but my coil pitch is equal to 15 slot only. It is given. So what is the chorded angle? It is 18 slot minus 15 slot. So the chorded angle is equivalent to the 3 slot. In term of slot, we just find out the value of 3 slot. It is a chorded angle. But we have to find out chorded angle in term of electrical degree, because in this formula we will use epsilon is equivalent to electrical degree. So we have to find out the slot angle. It is equivalent to 3 slot. So first find out the slot angle. What is the angle of single slot? And we know slot angle is 180 degree divided by slot per pole. Okay. So it is 180 degree. Total number of slot is 180. And what is the total number of pole? Total number of pole is 10 pole. So it is the 10 degree. Each slot is equivalent to 10 degree electrical angle. So the 3 slot is equivalent to Kundu, we are not discussing budget here. So don't copy paste budget highlight here. Some other time we can discuss the budget. So focus on the synchronous machine only. Okay. So 3 slot, one slot is equivalent to 10 degree. So 3 slot is equivalent to 30 degree. So what is the pitch factor? It is equivalent to cos epsilon by 2, cos 30 by 2. That is the 0.966. So now I find out the Kp. Just use this formula. So induced EMF in a coil. Induced EMF in a conductor, and we just find out induced EMF in a conductor was 10.65. That is the RMS value. So already we are getting the RMS value 10.65. Total number of conductor was 6 in a coil, and the Kp is 0.966. Do not forget to multiply it by the pitch factor. If you calculate, you will get the 61 point something, 61.72. Is it clear? How to find out the induced EMF in a coil? So whenever you are going to find out the induced EMF in a coil, always consider the pitch factor, but you don't need to consider the distribution factor, because the coil nothing to do with the distribution. Clear? Okay. Now I will tell you how to find out the induced EMF per phase. So I will using the same data in the question number 4, and by using the same data here you have to find out the induced EMF in a phase. We are using the same data, but here you have to find out the RMS value of induced EMF per phase. I am giving 4-minute time to solve this question, and your time start now. ये तीनों क्वेश्चन अगर आप कर लोगे तो आपको पता लग जाएगा कि इनमें डिफरेंस क्या होता है, एंड व्हाट इज द मीनिंग ऑफ डिस्ट्रीब्यूशन फैक्टर, व्हाट इज द मीनिंग ऑफ पिच फैक्टर, एंड वेयर वी शुड यूज द डिस्ट्रीब्यूशन फैक्टर एंड द पिच फैक्टर. Because most of the student every time use the pitch factor and the distribution factor, which is the wrong thing, because a single conductor does not have distribution factor and the pitch factor, and the coil does not have the distribution factor. You can also do this question directly by using the formula induced EMF per phase. And if you know how many coil a phase winding have, so by using the answer of previous question, you can also find out the induced EMF per phase. You are left with the 2 minutes. Two-layer winding we are using, and each coil has the 6-3 turn. Per phase, you have to find out the induced EMF per phase. I also take the power system, power electronics and electrical machine. A3672. $3539. That means 3540. Let's see whether it will happen or not. See, if you are talking about the induced EMF per phase, whether you will use pitch factor as well as distribution factor into account or not. In earlier question I told you about how the coil is formed. The coil have the large number of turn and each turn has the 2 conductor. This is my single coil and every coil has the 2 side. This is the one coil side and this is the another coil side. Suppose if we have a 2 or 3 coil, suppose if we have a 3 coil, just imagine we have a 3 coil. So this is my one coil. Each coil has the 2 side. This is my one side and this is the another side. No doubt the side may have large number of conductor because here in a side we have a 2 conductor, so it may have a large number of conductor. So this is my single coil. Then again I may have the second coil. Suppose this is my second coil. No doubt all is connected in series, and this may be the third coil. if one side of each coil is placed on a single slot and another side of each coil is placed in the another single slot, then it is called the concentric winding. But if these coil sides are distributed in the different slot, then it is called the distributed winding. So when we are talking about the winding, then you have to take the distribution factor into account if they are distributed throughout the air gap. If each coil side are placed in the different slot in the machine, then it is called the distributed winding. So when we are talking about the winding, we also consider distribution factor in addition to the pitch factor. Is it clear? So see, from directly the answer of this previous question, we can find out the answer of this question. Find out the induced EMF per phase. So first we have to find out, we know the induced EMF in a coil. So just find out how many coil we have in a phase winding. So we know what is the meaning of two-layer winding. What is the meaning of two-layer winding? Two-layer winding means, suppose we have a slot. This is a slot. If a slot contains two coil side means this is a coil side. This is my one coil side, and this is the second coil side of another coil. Both coil sides belong to the different coil. It is called the double layer winding. So in a double layer winding, or two layer winding, one slot have a two coil side. One slot have the two coil side. Clear? And in previous question I proved that one coil is equivalent to two coil side. Each coil has a two coil side. One is placed under the one pole and another is placed under the another pole. So one slot one coil is two coil side. So if right hand side are the same, two coil side, that means the left hand side should also be same. That means the total number of slot in this machine is equivalent to the total number of coil. So number of slot is equivalent to number of coil. Clear? How many slot we have? We have a 180 slot. If you have 180 slot, then the total number of coil in the alternator would be 180. This is the total number of coil. But we have to find out how many number of coil we have in a single phase winding. So number of coil per phase. In a single phase, how many coil we are using? If you divide by number of phase, so in a single coil, in a single phase, we have a 60 coil. Is it clear? We have a 60 coil. So we know the induced EMF in a single coil. If I multiply it by the 60 number of coil, I will get the total number of induced EMF in a phase. So total number of induced EMF in a phase, per phase. Induced EMF in a coil, we already calculated in the previous question, multiply by total number of coil in a phase. In a phase winding, how many number of coil we are using? So induced EMF in a coil, we calculated it was 61.72. It is the 61.72. Total number of coil in a phase, it was 60. It is 60 coil. But this is not the right answer, because it would be correct suppose if it were the concentric winding, but this is winding the distributed winding. So we have to consider the distribution factor into account. So we have to multiply by this term by the distribution factor. So it is the difference between where we have to use the distribution factor, we have to use the pitch factor, and where we don't use any pitch factor or distribution factor. So find out the distribution factor first. So the formula to find out the distribution factor is sin q gamma by 2 divided by q sin gamma by 2. Q is the phase spread, that is the slot per pole per phase. Total slot is 180, total pole is 10, and total phase is 3. So it has become 6. The 6 slots belong to the same pole and the same phase. And slot angle, the formula to find the slot angle is 180 degree divided by slot per pole. Slot is 180 degree, pole is 10. So the slot angle is equivalent to 10 degree. By using this value of q and gamma, you can find out the distribution factor. So finally the distribution factor is sin q gamma by 2. Q is the 6, gamma is 10 degree divided by 2. Q sin gamma by 2. If you calculate, you will get 0.956. Clear? So finally, induced EMF per phase 61.72 into 60 into KD, 0.956. If you solve this equation, you will get the 3540. So always remember, if question asks the induced EMF per conductor, don't use pitch factor or distribution factor. If in a question they ask about the induced EMF in a coil, then only use the pitch factor. If the question asks about the induced EMF in a winding or per phase induced EMF, then use both pitch factor as well as distribution factor. Is it clear? Three turn we already taken into account to find out the induced EMF per coil. In the previous question, when we are going to find out the induced EMF in a coil, we use this 3 turn into account. Or you can directly find out by using, you can directly solve this question by using this formula. See, I am solving it by the second method. Suppose if I go with the second method, because we know the direct formula to find out the induced EMF per phase. Is it clear? And this formula is under root 2 pi f NPH phi multiplied by kW. This is the direct formula to find out the induced EMF per phase. By using this formula, you can also find out the value of induced EMF. See, this is under root 2 into pi. We have to find out the value of frequency, number of turn per phase, flux we already find out, and the winding factor. So see, how to find out the frequency first. Find out the frequency. Frequency is Pn divided by 120. This is the frequency of induced EMF. 600 is given. 10 pole is given. 10 into 600 divided by 120. It is the 50 Hertz. Is it clear? Now how to find out the total number of turn per phase? Total number of turn per phase. So how to find out the turn per phase? It is the total turn divided by number of phase. Total turn in the machine divided by number of phase. Number of phase is 3. So how to find out the total turn? See, it has 180 slot, 2 layer and the 3 turn coil. In two layer winding, I told you one slot has the two coil side. We know the one slot has the two coil side, and the machine has 180 slot. So 180 slot, the machine will have 360, 180 into 2, 360 coil side. Is it clear? 180 coil side. This is the coil side, and we know one coil is equivalent to two coil side. Each coil has the two coil side. It is made from the two coil side. So 360 coil side means number of coil 360 divided by 2. So my alternator has the total 180 coil. Is it clear? Because in a machine we are using a 360 coil side and one coil has the two coil side. So total number of coils become 180 coil. So what is the number of turn per phase? It is 180 divided by total number of phase. It is the 60. So we have a 60 coil in a phase. Okay. Phi we already find out in this question. What was the phi? It was 0.096. 0.096. Sorry. Clear? And KW means pitch factor and winding factor. We already find out pitch factor and the winding factor. Distribution factor. Pitch factor, distribution factor we find it was the 0.956. So it is the 0.956. And the pitch factor we found 0.966. So now by using direct this formula, you can also find out the per phase induced EMF. Under root 2 pi, F was 50 and pH is 60. Phi flux per pole is 0.096. Pitch factor 0.966 into 0.956. So by using this formula, you can also find out the value of EPH. It would be same. So induced EMF per phase निकालना तो easy है, because you know direct formula. But always remember how the winding is formed. Winding is made from the number of coil. Each coil may have the large number of turn, and each one turn has the two conductor. Clear? Again you will get the same answer. Okay, so I am now moving to the next question. These all four questions is based on the how much the EMF is induced in a conductor, in a coil, in a winding. So now we are moving towards the next concept of synchronous machine. Okay, so this is my question number 5. A 60 kVA 220 volt 50 Hz 10 alternator has effective resistance of, sorry, it is a single phase alternator, not 10. Single phase alternator has the effective resistance of 0.016. Effective means the AC resistance, and the armature leakage reactance of 0.07. Compute the voltage induced in the armature when alternator is delivering half load at 0.8 power factor leading. I am giving you the 4-minute time to solve this question. Here the terminal voltage is given. 220 is the terminal voltage. Rating is always the terminal voltage. And you have to find out the induced EMF when half load is connected at 0.8 power factor leading. At the time of half load, it is a single phase alternator. So whatever the voltage is or current is given, it would be the single phase voltage and current. The resistance is given, leakage reactance is given. The resistance of armature winding and the leakage reactance of armature winding is given. In this question, they are asking about the induced EMF. It is not the excitation voltage EF, not excitation voltage. It is the induced EMF at the time of load condition, because the load is connected in the alternator. Terminal voltage is already given. You have to find out how much the EMF is induced in the alternator when it is delivering half load at 0.8 power factor leading. To 39.36. $216.21. Neeraj Kumar Maurya. You don't have to find out the EF. Again, I am telling you. You must know about the difference of excitation voltage, induced EMF, and the terminal voltage. The unit of all three quantity are the volt. Yes, only 7 seconds remain. 2 seconds, 1 second, and your time is finished. See, first let me tell you about the difference between the excitation voltage, induced EMF, and the terminal voltage. When you draw the equivalent diagram of an alternator, the equivalent diagram is always drawn on a per phase basis. This is the equivalent diagram of a alternator. EF is called the excitation voltage or induced EMF at the time of no load condition. XAR means the armature reaction reactance or the magnetizing reactance. JXAL, leakage reactance of armature, and the resistance of armature winding. So see, this at this point you This is the load terminal where you connect the load. This is called the load terminal voltage. This is the terminal voltage, and this is given, it is equivalent to the 220 volt. And the voltage at this point, it is called the E. So what is the difference between VT, EF and E? VT is the load terminal voltage. It is the voltage that is available at the terminal of alternator. EF is the no load induced EMF. That means it is the induced EMF when load is not connected. Load is not connected means when no current is flowing in the armature winding. So the effect of armature reaction is not there. EF is the no load induced EMF. It is called the no load induced EMF. It is also called the excitation EMF. When no load is connected in the alternator, then the EMF that would be induced would be equivalent to the EF. But this E is called the load induced EMF. When you connect the load in the alternator, at that time the EMF that would be induced, it will be the load induced EMF. Because when the load is connected, the current will flow in the armature winding, and when the current is flowing in the armature winding, the effect of armature reaction is also taking place. So this is the induced EMF when you are considering the armature reaction. EF is the induced EMF when the armature reaction is not there. So here you have to find out the induced EMF. That means you have to find out the E. It is not the excitation EMF that you have to find out. You have to find out the induced EMF. So half load is connected to the 0.8 power factor. So here I connect a load at the 0.8 power factor. So one load is connected here. Load is always connected at the terminal of alternator. This is the load. And this is only half load. That means the current that it will draw will be the half of the rated current. So first I will find out what is the value of rated current. So full load current means rated current. See, 60 kVA is the rating. When alternator were operated in rated condition, then it would give the 60,000 VA power, and the voltage here is the 220 volt. This is the 220 divided by 220. So it is the 272.2 ampere. This is my full load current. But here the load is the half of the rated load. That means the current that would flow will be half of the rated current. So at the time of half load, the current that would flow in the armature winding will be the half of the rated current. It is the 272.6 divided by 2. 272.2, that is, sorry. So it is the 136.1. This much amount of current is flowing here. So what is the value of E? See, if you use the phasor equation, this E is equivalent to VT plus voltage drop across RA plus XL. So it is the VT plus IA RA plus JXL. This is the induced EMF. This is the phasor equation. So either you can use this phasor equation directly if you are comfortable to deal with the phasor equation. If you are not comfortable to deal with the phasor equation, then you can also use the algebraic equation. What will be the algebraic equation of this phasor equation? It would be E square, in case of leading load, VT cos theta plus IA RA plus VT sin theta. For leading load, it is a minus IA XAL, not XS, because if you use XS here, you are going to find out the value of EF. So you can directly use this algebraic equation if you are not comfortable to deal with the phasor equation. So Vt is given, it is 220. Power factor cos theta is 0.8. Half load current means 136.1. Ra is given 0.016. Vt sin theta. If cos theta is 0.8, then sin theta is become 0.6. XL is 0.07. Just solve this equation. You will find out 216.21 volt. Is it clear? No doubt. You can also solve by using this equation. बट ध्यान रखिए जब आप फेजर इक्वेशन को डील करते हैं तो उसमें मिस्टेक होने की पॉसिबिलिटी ज़्यादा होती है एज कम्पेयर टू एल्जेब्रिक इक्वेशन. व्हेन यू डील विद द फेजर इक्वेशन, ऑलवेज टेक वन क्वांटिटी एज ए रेफरेंस क्वांटिटी. टेक Vt as a reference quantity. Then for other phasor quantity like Ia, you have to take the magnitude as well as the phase angle of this quantity. ठीक है. So always remember, in this question you are not going to find out the value of EF, you are going to find out the value of E. अगर आपको EF निकालना होता तब आप यहां पर you use the, in place of XL you would use XS. Okay, so I am moving to the next question. This is the question number 6. From the following test data, determine the voltage regulation. In this question, you have to find out the voltage regulation of a 200 volt single phase alternator delivering 100 ampere current at 0.8 power factor lagging. The open circuit test data is given. The 500 volt is produced, that is the open circuit voltage when the field excitation is the 5 ampere. In case of short circuit test, 100 ampere short circuit armature current would flow if you are applying the 2.5 ampere of field excitation. What is the value of voltage regulation? You have to find out the voltage regulation when 100 ampere current is flowing at the 0.8 power factor lagging load. Clear? You have to find out the value of voltage regulation when the alternator is delivering 100 ampere current at 0.8 power factor lagging. The open circuit test and the short circuit test data is given. By using open circuit test data and the short circuit test data, you can able to find out the value of synchronous impedance ZS. So sorry, just a minute. In this question, RA is also given. The RA is given. RA is 0.8 ohm. The resistance of armature winding is given, it is 0.8 ohm. By using the open circuit test and the short circuit test data, just find out the value of synchronous impedance. Synchronous impedance, you know, RA is known. Find out the value of XS. Then by using RA and XS, find out the value of voltage regulation. B, 21.6%. Still you are left with the 1 minute 7 seconds. This question is based on how to find out the voltage regulation of alternator. Voltage regulation means the change in the voltage when load is changed. How much the voltage will increase or decrease when you suddenly remove the load. B, Neeraj Kumar Maurya. 21.6 is the correct option. It is a single phase alternator, not the 3-phase alternator. Always see this, whether it is a single phase or 3 phase. ये मिस्टेक कर देता है, ध्यान रखिए, ये बहुत छोटी सी मिस्टेक है जिससे आपकी गलती हो जाती है. निसी C, 8.32 is the correct option. Yes, anybody? Do you need more time? Okay, let me solve this for you. Tell me how to find out the value of ZS. By using open circuit test and the short circuit test data, you can find out the value of ZS. Is it clear? So how to find out the value of ZS? We draw the open circuit test and the short circuit OCC and SCC on a same graph paper. To find out the value of ZS, we draw the OCC and SCC on the same graph paper. Suppose this is my OCC. In OCC, after some time, the saturation will occur. Clear? This is the OCC. But SCC is always a straight line. This is a straight line. So I have drawn OCC and SCC on the same graph paper to find out the value of ZS. So what is the formula to calculate the value of ZS? Formula to calculate the value of ZS is open circuit voltage. That means EF. Divide by short circuit current. If you divide open circuit voltage by short circuit current, but always remember here that IF should remain constant. We are not changing the field excitation. IF is the same. With the same value of field current, you have to see the open circuit voltage and the short circuit current. So see, at the field current of 0.5 ampere, sorry, not 0. It is a 5 ampere. The open circuit voltage is the 500 volts. Suppose at the field current of 500 ampere. This is my 5 ampere field current. Clear? Open circuit voltage is the EF. This is IF. EF versus IF is the OCC. And short circuit armature current versus field current is the SCC. So at the 5 ampere field current, the open circuit voltage here, it is equivalent to 500 volts. Suppose it is the 500 volt. But it is given at the field current of 2.5 ampere, the SCC is 100 ampere. So SCC is not given at the 5 ampere, it is given at the 2.5 ampere. Is it clear? So at 2.5 ampere, this current is given, it is the 100 ampere. Since SCC is a linear characteristic, so at the 5 ampere, what would be the IASC? It would become 200 ampere. Is it clear? Because the relationship between IA and IF is a linear in nature. So at the 2.5 ampere field current, if armature current is the 100 ampere, then at the 5 ampere of field current, the armature current would become 200 ampere. So now at the same value of field current, we know the open circuit voltage, that is the 500 volt, and we know the short circuit current at the, this is the 200. So ZS is the 2.5 ohm. यहाँ पर जो सबसे ज़्यादा मिस्टेक होती है, लोग डायरेक्टली इसको इससे डिवाइड कर देते हैं. In this formula, when you are going to find out the value of ZS, the IF should be constant. So find out the open circuit voltage as well as short circuit current at the same value of field current. This is the common mistake that most of the students do. So if you know the value of ZS, you can find out the value of XS. ZS is 2.5, RA is 0.8. You will get 2.36. XS is the 2.36 ohm. So what is the voltage regulation? What is the formula to calculate the voltage regulation? It is no load voltage EF magnitude versus at particular load voltage divided by VT. How much voltage is changed when you remove the load? So VT is given at the 100 ampere, the VT is given, it is the 2000. Just we have to find out the value of EF. So you can find out the value of EF either using the phasor equation. Phasor equation is the VT plus IA RA plus JXS. Either use this phasor equation or you can also use the algebraic equation. If you are not comfortable with the phasor equation, to deal with the phasor equation, then you can use the algebraic equation. As per the algebraic equation, EF square is the VT cos theta plus IA RA square plus VT sin theta plus IA XS square, because it is a lagging nature of load. Clear? So VT is 2000, terminal voltage is the 2000. Cos theta is given 0.8. IA, at which current you have to find out the value of EF? 100 ampere. RA is 0.8 plus VT 2000. If cos theta is equivalent to 0.8, then the sin theta would be 0.6. XS we just find out 2.36 square. If you calculate EF, you will get that 2210. So 2210 is the no load induced EMF, 2210. Now put this value of EF in the formula of voltage regulation. So the voltage regulation is become 2210 minus 2000 divided by 2000 into 100. If you calculate, you will get 10.50%. So the voltage regulation of alternator is the 10.50%. Clear? So where you are committing the mistake? Where you are committing the mistake? To find the value of ZS. Always remember, अगर छोटी सी चीज भी अगर आप भूल जाते हैं ना, if you don't know that this equation is valid only when IF is equivalent to constant, you would get the wrong answer. ठीक है? So always remember, when you find out the value of ZS, the open circuit voltage oblique short circuit current, it is at the same value of field excitation. हाँ, मेरे को पता था, maximum student will take it as a 100 because they just know EOC upon ISC. But you have to take IF is equivalent to constant. If IF is the different at the time of open circuit test and the short circuit test, just find out the value of ISC at the time of same excitation, field excitation. Clear? Are you getting some new concept before the gate exam? So I move to the question number 7. A 1200 kVA 6600 volt. It is a 3-phase star connected, not single phase, 3-phase star connected alternator with resistance of armature winding is given 0.4 and the synchronous reactance is the 6 ohm per phase. Deliver the full load current at the 0.8 power factor lagging and the normal rated voltage. What will be the terminal voltage for the same excitation and the load current of 0.8 power factor leading? Sorry, it is the leading. आपको लैगिंग क्यों पता है और लीडिंग के ऊपर आपको फाइंड आउट करना है. I am giving more than 4 minute time because it may have some calculation. Okay, your time is start now. When full load and 0.8 power factor lagging load is connected, then the terminal voltage is the rated voltage. But what would be the terminal voltage if the excitation is same, but instead of using 0.8 power factor lagging load, if you use the 0.8 power factor leading load? जीरो पॉइंट एट पावर फैक्टर लैगिंग लोड के टाइम पर आपको रेटेड वोल्टेज मिल रही है, लेकिन अगर आप लीडिंग लोड लगाएंगे तब कितना वोल्टेज आपको मिलेगा? Hi Gauri. It is a 3-phase alternator, so convert every quantity into the per phase quantity first. The first thing that you have to see in the numerical is that whether it is a 3-phase machine or a single phase machine. If it were the 3-phase machine, always convert every quantity into the per phase quantity. You still have 1 minute and 41 seconds. Fifty seconds left. In both the condition, the excitation is the same. We are not changing the excitation. Neeraj A 4560. You are doing a very silly mistake here. Okay, suppose in a question, if the question asks about the terminal voltage in case of three-phase alternator, your answer will be on the per phase basis or it will be the line voltage. In three-phase quantity, always each quantity is given will be the line voltage, line current. और अगर आपको जो निकालना है, it should also be the line voltage. So see, initially the 0.8 power factor lagging load was connected. So when 0.8 power factor lagging load is connected, B, yes, B is the correct option. Lagging load is connected. The terminal voltage is the rated voltage. Clear? Rated voltage, that is 6600 volt. So it is giving terminal voltage equivalent to the 6600 volt. 6600 volt, it is the line voltage. So in case of star connected alternator, I will divide it by the √3 to find out the per phase voltage, because the formula is applicable only the per phase quantity. So it is the 3810.5 volt. This is my per phase terminal voltage, and since it is operating at the full load, so find out the full load current. Full load current, how much current is flowing? Full load means rated current. The rating is given 1200 kVA. kVA means multiply by 1000, it is become VA. 3-phase kVA is the √3 VL into IL. So √3 line voltage is the 6600 volt. So we will get the line current. √3 VL IL is the kVA. If you solve this equation, you will get 105 ampere. In case of star connection, this line current is the same as the phase current. So this is also the phase current. In star connection, line current and the phase current are the same. So we know the value of current and the value of terminal voltage. By using these two quantity, we can find out the excitation EMF, EF. I am using here the algebraic equation Vt cos theta plus IARA plus Vt sin theta plus IAXS, because the load is lagging in nature. So here it will be the all quantity will be the positive quantity. Vt is the 3810.5, cos theta is 0.8, IA is 105, RA 0.4, axis is the 6, 0.4. Vt sin theta 3810.5. If cos theta is 0.8, then the sin theta would be 0.6. IA x is the 6 square. So from this formula we can calculate the value of E. It is the 4250. No doubt it is on the per phase basis, because this equation is always on the per phase basis. Do not apply this equation directly on the line voltage and the line current. Always apply this equation on the per phase voltage and the per phase current. So this is my excitation voltage. See, if the excitation is remains same, that means the current in the rotor winding or the field winding is the same. If excitation is same, that means the excitation voltage will be same. because the EF depend upon the field winding of flux or the field winding of current. It would be 4250 for second case 2. Now, if load is 0.8 power factor leading, in place of lagging load, if I apply 0.8 power factor leading load, then what will be the terminal voltage? That we have to find out. So again, I am using the formula for the leading load. The formula for the leading load will be the same, only here in place of positive sign we will use negative sign. So the EF square Vt cos theta plus IARA square Vt sin theta minus IAxis. In case of leading load, it would be negative. EF is 4250. Vt terminal voltage you have to find out. Cos theta is 0.8. IA, again you have to find out full load current. Current is the same, 105. Vt sin theta minus IAxis square. This will be a quadratic equation in terms of Vt square. You have to solve this quadratic equation to find out the value of Vt. When you solve this quadratic equation, you will get the 4560 volt. But this 450 volt is the per phase voltage. In a 3-phase alternator, whenever they ask about the terminal voltage, you have to give answer only line voltage. ध्यान रखिए, इस तरह की silly mistake नहीं होनी चाहिए. So line voltage would be the root 3 times of the phase voltage. It would be the 7900. Clear? For the 3-phase alternator, always the answer should be in terms of line voltage. Whatever the quantity is given, it would always be the line voltage and the line current. और अगर आपको पूछा है तो वो भी लाइन वोल्टेज या लाइन करंट ही पूछा होगा. क्लियर? Excitation is same means the excitation voltage would remain same. It will not be changed. क्लियर? सो हमेशा ये 3 फेज या सिंगल फेज जरूर देखिए, इसमें एक मिस्टेक नहीं होनी चाहिए. ये तो बहुत सिली मिस्टेक होगा अदरवाइज. Okay, now moving to the question number 8. Two 3-phase 6.6 kV star connected alternator. We have a 2 alternator. Both are connected in the star. They supply a load of 3000 kV at 0.8 power factor lagging. This is my combined load. The synchronous impedance of alternator A is given 0.5 plus J10, and for the machine B is 0.4 plus J1.2. The excitation of machine A is adjusted so that it delivers 150 ampere at a lagging power factor. A alternator is giving 150 ampere at the lagging power factor, and the governor are so set that the load is shared equally between the machine. That means the machine A and the machine B, they are providing the same amount of active power to the load. What is the load angle? Means the delta of machine B will be. What is the load angle of machine B? Delta. Again, I gave you more than 4 minute time to solve this equation. And your time start now. Two alternators are connected in parallel and both are supplying the load of 3000 kilowatt at 0.8 power factor lagging. The synchronous impedance is given for both machine A and machine B. The excitation of A is adjusted so that the alone A machine is giving 150 ampere current at the lagging power factor, and the governor are so set that both machine A and B, they are sharing the load equally. That means they are providing the same amount of active power. So what is the load angle delta of the machine B? .6 kV. Again, it is a three-phase alternator. So convert each quantity into the per phase basis. You can take the terminal voltage as a reference. This question is based on the parallel operation of alternator. ZB is given, na? ZA is 0.5 plus J10, ZB is given. The impedance is given for both the machine. For both machine, the impedance is given. Okay, nobody answer this question. $60. No, 60 degree is the wrong answer. See, two alternators, they are connected in parallel and they are supplying power to a load, and the load has the 3000 kilowatt at 0.8 power factor lagging. Since both generators are connected in parallel, so their terminal voltage will be the same. It is the 6.6 kV. So first I am going to find out the overall load current. Overall load current. See, terminal voltage is given 6.6 kV means 6600 volt divided by root 3 per phase quantity, because it is a three phase machine. So it is approximately 3810 volt. 3810 point something aata hai. I am taking 3810 volt. This is my terminal voltage. Okay. If I take VT as a reference, terminal voltage is a phasor quantity, and among all the phasor quantity, we take one phasor quantity as a reference quantity. That means we have to find out all other phasor quantity with respect to Vt only. This is the Vt. Now how much the current, the overall load is drawing, because overall load has the 3000 kilowatt at 0.8 power factor lagging. Total load is 3000 kilowatt. And this much amount of load is given by both the machine. 3000 kilowatt means 3000 into multiply by 1000 watt. For the three phase power I am using this formula root 3 VL IL cos theta. VL means line voltage. Line voltage is the 6600 volt. IL into cos theta. What is the load power factor? It is the 0.8 power factor. If you calculate, you will get the value of I. I you will get, it is the 328 ampere. This is only magnitude of load current. If I taking Vt as my reference phasor, this is the Vt. So the current is lagging by voltage. If this is the Vt, the current is lagging the voltage. It is 0.8 power factor lagging. That means this angle is the cos inverse 0.8. So what is the current phasor? Magnitude is the 328, but angle is minus cos inverse 0.8, that is 36.36 something. If you convert this polar quantity into the rectangular quantity, you will get 328 0.8 minus j 0.6. It is the 262 minus j 195. This is the total value of load current. Is it clear? Total load current, which is given by alternator A plus alternator B simultaneously. Okay, now find out how much the current is given by the machine A. Machine A is delivering 150 ampere of current at the lagging power factor. What is the angle of lagging power factor? It is not given. So for machine A, see, the governor are so set the load is share equally. Load is share equal means both machine A and B, they are providing half of the load. Total load is the 3000 kilowatt. So each generator is giving 1500 kilowatt of power. If I know the total power delivered by the machine A, then it is equivalent to the root 3 VL. VL is the same because both machine is operating in parallel condition, so the voltage will be the same. Current is given, machine is given 150 ampere current, but we do not know about the power factor, so we can find out the power factor of machine number 1. If you calculate, you will get cos phi 1 is equivalent to 0.874 or phi 1 is equivalent to 29 degree. Clear? So what is the current given by the machine A? I1. Magnitude was 150 ampere, but angle you got the minus 29 degree because it is a lagging power factor. It is given lagging power factor, but magnitude of power factor was not given. Okay. So if you calculate this value of I1, you will get 131 minus J 72.6. Is it clear? So what we got the current supply by the machine number A and the current supply by the machine number A plus machine number B. EF VT cos delta से हम लोग क्यों नहीं कर रहे हैं? Because here resistance is also given. EF VT cos delta is applicable when you neglect the value of armature resistance. Is it clear? So that formula is applicable only if the armature resistance is neglected, but here armature resistance of both machine is given. For machine A it is 0.5 and for machine B it is the 0.4. So see, we know the total current and we know the current supply by the machine A. So we can find out the current supply by machine number B. So current supplied by machine number B. By machine B. Current supply by machine number B will be total current multiplied by I1. Total current 262 minus J 195. I1 is 131 minus J 72.6. So by using this formula, you can find out the value of I2. It would come 131 minus J 124.4. This is the value of current supply by the machine number B. Okay. Now find out the induced EMF in machine number B. That is the excitation EMF. EB. It would be VT plus I2 multiplied by ZB. Terminal voltage is the same, 3810. I2 is 131 minus J 124.4. ZB is given 0.4 plus J 1.2. Calculate. It would come 5350 plus J 1520. EF, this is the excitation EMF of the machine B. Okay, now see, we have taken VT as a reference quantity. That means we assume the angle of VT as a 0. Now we know this EB, the angle of EB. So what is the angle of EB? The angle between VT and E is only the load angle. Is it clear? So suppose if this is my EB, so angle between EB and VT, it is the load angle only. The angle of VT is the 0, so the angle of EB will be the load angle delta B. So load angle delta B, how to find out? The tan inverse imaginary number divided by the real number. It will come 15.9 degree. Because load angle is nothing but the angle between terminal voltage and the excitation EMF. So VT is equivalent to 0. The angle of VT is the 0 because we have assumed VT as a reference quantity. So whatever the angle of EB has, it has the load angle. तो आपको वाला फॉर्मूला नहीं यूज करना है जो अभी आप बात कर रहे थे. दैट फॉर्मूला इज एप्लीकेबल जब आपका आरए नेग्लेक्टेड होता है. लेकिन यहाँ पर अगर आपको आरए दिया हुआ है तो आप डायरेक्ट उस वाले फॉर्मूले से नहीं निकाल सकते, वो आपको गलत आंसर देगा. क्लियर? यू विल गेट द रॉन्ग आंसर. Okay, should I move to the next question? चलिए, now we come to the question number 9. This is the last class of electrical machine because we have already completed all three machine, transformer, induction, DC, and this is the last fourth one. We can take the similar class for power electronics. Okay, this is the question number 9. A cylindrical rotor synchronous motor with excitation EMF is given 1.5 is connected to the infinite bus bar. The axis means the synchronous reactance is given 1.2 pu and the output power delivered to load is the 0.5 pu. What is the magnitude of reactive power delivered oblique absorbed by the synchronous motor? The active power, it is delivering the active power equivalent to 0.5 pu. How much reactive power it is delivering or absorbing? I am giving you a 4-minute time again, and your time starts now. Cylindrical rotor synchronous motor is given. Excitation EMF is given. It is connected with the infinite bus bar. The value of synchronous reactance is given. The cylindrical rotor synchronous motor is delivering 0.5 pu of power. You have to find out the magnitude of reactive power delivered oblique absorbed by the synchronous motor. No doubt, DC is the easiest of electrical machine and the synchronous is the toughest of electrical machine. The toughest topic of electrical machine is the synchronous machine. Shivam, how are you? The alternator is delivering 0.5 pu of active power. Sorry, it is synchronous motor, not the alternator. It is a synchronous motor. So how much active or reactive power is delivered oblique absorbed by the synchronous motor? See, what is the difference between the induction motor and the synchronous motor? Induction motor always draw the reactive power from the supply because it draw the reactive power from the supply to create the rotating magnetic field. But depending upon the excitation, the synchronous motor can either deliver the reactive power, it may also absorb the reactive power, or it is possible it neither deliver nor absorb the reactive power. So all three cases possible. A, it absorbs 0.3125 at per nearest, C 0.3125. All three possibility may be possible in case of synchronous motor. It may either deliver, it may absorb, or neither deliver nor absorb. Active power is given, reactive power you have to find out. It is taking 0.5 pu active power from the supply. No doubt it is a motor, so it will take the active power from the supply. Every quantity is given in the pu basis. I think you are not able to solve this. Okay, let me do this question for you. Synchronous motor is connected with the infinite bus bar. What is the meaning of infinite bus bar? It is like our power system which have the constant voltage and the constant current. This is my infinite bus bar. In term of pu value, the infinite bus bar voltage is equivalent to the 1 pu. It is a 1 pu. Motor is connected. The excitation EMF of motor EF in term of pu is the 1.5 pu, and it is taking active power because motor will always take the active power, that is equivalent to 0.5 pu. So both for motor and generator, the active power equation P is equivalent to, if you neglect the value of resistance, then EF Vt divided by XS into sin delta. This equation is valid if armature resistance is neglected, because in this question R is not given. That means you have to neglect the value of Ra. So P is 0.5, EF is 1.5, Vt is 1, XS is 1.2, XS is 1.2, multiply by sin delta. If you solve this equation, you will get the sin delta equivalent to 0.4. If sin delta is 0.44, you can also find out the value of cos delta, 1 minus sin square delta. It will come 0.9165. So now we have the value of sin delta as well as cos delta. Clear? Okay. Now what is the formula of reactive power in case of synchronous motor? In synchronous motor, this is the formula of reactive power, Vt square upon XS minus EF Vt XS into cos delta. If you take Vt upon XS as a common term, this equation has become Vt minus EF cos delta. As per this formula, the direction of reactive power is this. As per this formula, that means we are assuming that motor is taking active power as well as reactive power. So just put the value here. Vt is 1, EF is 1.5, cos delta we just find out 0.9165. Divide by XS. XS is 1.20. If you solve, you will get minus 0.3125. It is in term of minus. Minus means it is opposite to my reference direction. So it is not taking the reactive power. It is giving the reactive power. Negative means it is giving the reactive power. 3.215 pu. It deliver 0.3125 pu reactive power. Is it clear? Negative sign represent that the direction of Q is opposite to my reference direction, and we assume that we are taking active power as well as reactive power from the supply. Clear? Okay, so now we move to the next question. It is a question number 10. A 3-phase 2000 kVA 11 kV star connected alternator has the following data. Coal loss is given 14 kilowatt, copper loss is given 10 kilowatt, friction and window loss is given 16 kilowatt, field winding resistance is given 0.13, for field current of 110 ampere. The alternator efficiency at the rated 0.8 power factor lagging would be. So since it is not visible, I am writing option here. A option is 96.12, B option is 95.12, C option is 97.12, and D option is 98.12. So losses is given. You have to find out the alternator efficiency at the rated load and 0.8 power factor lagging. So this is the question on the efficiency of alternator. You must know about the power flow diagram of the alternator to find out the efficiency. We are covering each and every concept on which the question may be asked in the examination. So this is on the concept of efficiency of alternator. Copper loss is given at the current of 90 ampere. Field winding resistance is the 0.31. The field current is flowing, it is the 110 ampere. You have to find out the alternator efficiency at rated load and 0.8 power factor lagging load. C 97.12. As per Prakash, C is the correct answer. Thank you. Yes. This was our main motto, so that your complete syllabus will be revised through these problems. And we try to cover each and every concept of the electrical machine. We try to cover the question from each and every concept. Still you have 2 minutes. How to find out the efficiency? You have to find out the efficiency at the rated load. So at the time of rated load, the output power is given, output kVA is given basically. Just find out the input power, output power divided by input power, it would be the efficiency. You have to find out the all losses when rated current is flowing and the current in the field winding is 110 ampere. So the current in the field winding is 110 ampere and current in armature winding is rated current. D 98.12. As per Neeraj it is D, as per Prakash it is C. Still you have 56 seconds. Okay, now Neeraj has changed the answer. He is opting for C. As per Bevav, the answer is C. Field current means the current that is flowing in the rotor winding. Armature current means the current that flows in the armature winding. Okay, so your time is up. Now I am going to solve this question for you. See, 2000 kVA is the rating. It is at the time of rated load. The alternator would provide 2000 kVA and the power factor of load is the 0.8. So what is the output power at full load condition? output power at full load condition. Power is always in the term of active power. So it is volt ampere multiplied by cos theta. So 2000 multiplied by 0.8, because the load power factor is the 0.8 power factor. You will get the 1600 kilowatt. This is my output power at the time of full load. Now I am going to find out the overall losses. So first I will come to the copper loss in the field winding. The field winding is placed on the rotor. So copper loss on field winding, DC current flow in the field winding, it is equivalent to I square multiplied by resistance of field winding. So 110 ampere current is flowing, 110 ampere DC current is flowing in rotor winding, and its resistance is 0.31. It is 0.31. So it is 3.751 kilowatt. I have converted into the kilowatt. This is the copper loss in the field winding. Now we have to find out the copper loss in the armature winding. We know the copper loss at the 90 ampere current is the 10 kilowatt, but we have to find out the copper loss when the full load current is flowing in the armature winding. So first find out what is the value of full load current. So full load current means the current that would flow in the armature winding when armature is delivering the rated amount of kVA, that is the 2000 kVA. So it is the 2000 kVA. It is 3-phase kVA. 3-phase kVA is equivalent to root 3 VL into IL. VL, it is the 11 kV. So you will get the value of line current. And in case of star connection, line current and phase current is the same. It is the 104.97 ampere. So this is my full load current. We know the copper loss in armature winding when 90 ampere current is flowing. So you have to find out what would be the copper loss when 104.97 ampere current is flowing. So copper loss in armature winding. Armature winding means the winding that is placed on the stator. When 90 ampere current flow, it is given in the question, it is 10 kilowatt. So what will be the copper loss when full load current flow? Full load current is 104.97. We all know the copper loss is proportional to current square. So it would be 104.97 divided by 90 into square. So the copper loss will be 13.60 in term of kilowatt. This is my copper loss. So what will be the total losses? See, all these losses given on the for 3 phase. So in armature winding, the copper loss is the 13.60. Field winding copper loss is 3.751. Now core loss does not depend upon the current. It will remain same, 14. Friction and windage losses remain same. It is a 16. So total loss will come 47.351 kilowatt. Now what is the input power? Output power plus losses. Output power is 1600 kilowatt plus 47.351. So it is 1647.351. Clear? So what is the efficiency? Output power divided by input power. $1,600 divided by 1647.35. You will get 0.97125 or 97.12%. सिर्फ दो चीजें आपको ध्यान में रखनी थी. The copper loss is proportional to current square. If the copper loss is given on a particular current and you have to find out the copper loss on another current, then you can first find out it is proportional to current square. Similarly, you have to also find out the value of copper loss in the field winding, because some loss is also taking place in the field winding. लास्ट 7 डेज में अब आप बहुत ज़्यादा कुछ नहीं कर सकते. अपने दिमाग को शांत रखिए और जो भी आपने शॉर्ट नोट्स बनाए उससे थोड़ा आप रिवीजन देखते रहिए और कुछ भी नया करने का ट्राई मत कीजिए बहुत ज़्यादा. डोंट स्टार्ट द न्यू टॉपिक. ओके, नाउ वी मूव टू द नेक्स्ट क्वेश्चन. Now we come to the question from the salient pole synchronous motor or the salient pole synchronous generator. The salient pole synchronous motor has xt equivalent to 0.8, xq equivalent to 0.6. It is connected with the rated supply and delivering the rated power. What is the excitation EMF EF if motor operate at 0.8 power factor leading? Assume losses to be 0. All data is given in PU. Again, I give you 4-minute time to solve this question. XD, XQ is given. Either you can use the tensai method or you can use the EF dash method, whatever you like. I generally solve this type of question with the EF dash method, but you can also use the tensai method. It is a synchronous motor, not the synchronous generator. This is the area of the salient pole machine where most of the student does not pay attention. We mostly devoted our time just to solving the cylindrical rotor machine problem. So whatever method you like, you can solve either using the tensai formula or by using EF dash method. I generally solve this type of problem by using the EF dash method. So 2 seconds left. B 1.442 minus 56.3. It is connected with the rated supply, means the terminal voltage equivalent to the 1 pu. Yes, how to solve the salient pole machine problem? The most toughest topic of synchronous machine. Okay, your time is up. Let me do this for you. See, I'm coming step by step method. The first step. In first step, we just find out the value of EF dash. So use the same step. Only जो थीटा है उसको आप लैगिंग के लिए यूज करिए. ठीक है, इस तरह के बहुत सारे क्वेश्चंस एग्जाम में आए हुए गेट एग्जाम्स के अंदर, और मोस्टली लोगों को इसमें प्रॉब्लम आती है जब ये सेलिएंट पोल मशीन के क्वेश्चन आपको बोलते हैं. ठीक है, so now I am moving to the question number 12. It is the same data is given. XD is given. XQ is again 0.6 pu. It is delivering the rated supply, rated power, but here the load is 0.8 power factor lagging load. No doubt we are using the motor. Use the same step just for the lagging load, and your time starts now. Still you have a 2 minute 54 second. Question not clear. XT and XQ is the same. Question is same. Only in place of lagging load, sorry, leading load, it has the lagging load. Still you have 1 minute. I ask them to start the power system. They must decide whether they want or not. You're left with the 9 seconds. Okay, your time is up. Now I am showing how to do this question. Again, what is my first step? In the first step, we will going to find out the value of EF dash. EF dash is, again, this is the synchronous motor. So it is the Vt minus IaRa minus JIa XQ. Since Ra is not given, so it would be only Vt minus JIa XQ. If I take Vt as a reference quantity, so it is the Vt 1 angle 0 degree minus J. What is the Ia? Ia is 1 ampere again, but here current is the lagging in nature. So here we use the plus 36.86. Here I will use minus 36.86. As compared to my voltage, the current is lagging. Current lagging means the angle of current will be negative as compared to voltage. It is at minus 36.86. XQ. XQ is again 0.6. So it is become 1 minus 0.6. Angle is become J is 90 degree, 53.14. If you solve this, you will get 0.64 minus J 0.48. This is the value of EF dash. Magnitude is come 0.8 and angle is minus 36.86. I told you the angle of EF dash is nothing but the delta. So this is my delta. So you can say the magnitude of EF dash is 0.8 and angle delta is minus 36.86. No doubt, in case of motor, the delta should always be in negative number, because the load angle is negative for synchronous motor and load angle is positive for synchronous generator. Now, what is my second step? In the second step, I will find the inner displacement angle. It is the delta plus theta. Why I am using plus positive here? In earlier question, I used negative minus theta because here the load was lagging in nature. Here load is leading in nature. So it is minus 36.86. What is the theta? Theta is also 36.86. 0.86 power factor. So the size becomes 0. The angle size become 0. This is the second step. Now the third step, find out the current along the direct axis. It is the Ia sin psi. Since psi is 0, so whatever the value of Ia, it would always be the 0. And finally, the magnitude of EF is nothing but the magnitude of EF dash minus, in case of motor use ID negative, XT minus XQ. ID is 0, so it is equivalent to EF dash only. And EF dash we calculated, it's the 0.8. So my final answer, EF is magnitude is 0.8 and its Angle is minus 36.86. So A is the correct options. You can also try the same type of question for synchronous generator. It is for the synchronous motor. In case of synchronous generator, here we use the positive. And in synchronous generator, the delta would come always positive. Okay, now moving to the next question. This is the question number 13. A three-phase star-connected alternator is delivering 50 megawatt, 20 megawatt and 8 MVR to infinite bus at 11 kV. The alternator has the synchronous reactance of J0.3. The excitation EMF of alternator is, what is the value of EF? You have 4 minutes time to solve this question. You have to find out the value of excitation EMF. Alternator is delivering 20 megawatt of active power and 8 MVR of reactive power at 11 kV voltage. The synchronous reactance is J0.3. What is the value of EF? After this, we have 2 more questions. Yes, active and reactive power is given. Synchronous reactance is given. Voltage is given. Find out the excitation EMF in case of alternator. The alternator is giving 20 megawatt of active power and 8 MVR of reactive power at 11 kV voltage. The synchronous reactance is J3. What is the excitation EMF EF? Use the formula of active power and reactive power. Nobody have done? Still you have 40 seconds. EVX sin delta is, yes, it is a P active power. Similarly, use the formula of reactive power. for alternator. And by using these two formula, find out the value of EF. Excitation voltage means the EF. Okay, see. (11 kV) is the no doubt, it is a line voltage. What is the formula of active power? P. It is EF VT divided by XS into sine delta. If you use line voltage here, you will get the three-phase power. If you use the phase voltage here, you will get the single phase power. So I can use directly line voltage here to get the three-phase power. Clear? So P is the 20 megawatt. This is the three-phase. No doubts. Unit is the megawatt, so don't need to write this unit. It is EF VT XS into sine delta. This is equation number 1. Now what is the formula to find out the value of reactive power? It is EF VT divided by XS into cos delta minus VT square divided by XS. Divided by XS. So what is the reactive power? Reactive power is the 8 MVAr. EF VT XS cos delta. VT is the terminal voltage. It is given. Terminal voltage is the 11 kV. If I use direct line voltage, I am getting the three-phase reactive power. XS is given. It is the 3. It is 3. So from this equation, I can find out the value of EF VT XS into cos delta. If you find, it will come 48.33. This is equation number 2. So now we have equation number 1 and equation number 2. If I divide equation number 2 from the equation number 1. So divide equation number 2 by equation number 1. EF VT XS will be cancelled out. Sine delta divided by cos delta. Actually it is EF VT XS into sine delta divided by the EF VT XS into cos delta. Sine delta cos delta 20 upon 48.33. EF VT XS you can cancel out. So it is become 10 delta is equivalent to 0.4138. If you divide 20 by 48.3, you will get the 0.4138. So from this we can find out the value of delta, that is the load angle. It is the 22.48. This is my load angle. But we have to find out the value of EF. Now if I put this in equation number 1, we know the equation number 20. EF VT. VT is the 11 kV. XS is 3. Delta we just find out 22.48. Clear? P equivalent to EF VT XS into sine delta. From this equation, I can find out the value of EF. It is always the line voltage because I am using the all formula into the three-phase basis. This formula is applicable on per phase quantity as well as the line quantity. If you use the line quantity, you can get the three-phase power. If you use the phase quantity, you will get the single phase power. So 14.265 would be the right answer. Clear? So what is the correct answer? B was the correct answer. Now I am coming to the second last question of this class. For a 6-pole 50 Hz 42 slot alternator which has 2-layer winding, what is the distribution factor? Just find out the distribution factor if 2-phase winding is used and narrow spread coil is used. This question I have intensely used because you must know how to find out the distribution factor for a fractional slot winding. This is an example of a fractional slot winding. It is an example of a fractional slot winding. How to find out the distribution factor for a fractional slot winding? Which formula we have to use? We may have two types of winding, integral slot winding and the fractional slot winding. Now I am giving a 2-minute time because already I have given so many time. So within 2-minute time, try to solve this question. It is a second last question. C 0.873. Any other answer? No doubt it is a 3-phase . Two-phase winding, sorry, it is a 2-phase winding, not 3-phase. C. How to find out whether it is a fractional slot winding or integral slot winding? If slot per pole, per phase, it is an integer number, then it is called the integral slot winding. If it is a fractional number, it is a fractional slot winding. Total number of slot is 42 slot. Total pole is the 6 pole and total phase is the 2 phase. So we'll get the fractional number. That means it is a fractional slot winding. Yes, A is the correct option. So it is example of fractional slot winding. Is it clear? In case of fractional slot winding, first we find out the value of SK, slot per phase, divided by the pole. Both should be the integer number. Slot is the 42 and phase is 2 and pole is 6. No doubt the numerator is integer number, it is 21. Denominator is also integer number. So slot per phase should be integer number and the pole should be integer number. Now I will find out what is the common factor between the numerator and denominator. What is the common factor? 3 into 7 and it is a 3 into 2. So 3 is the common factor. Between numerator and denominator, the 3 is the common factor. If you remove the common factor, then numerator has become 7, denominator has become 2. So it is my Sk oblique Pk. It is called the Sk upon Pk. Sk is 7, Pk is 2. So Sk is 7. This is called the Sk upon 7. Just find out the maximum common factor between the numerator and denominator. Whatever will be left, it will be the Sk. Now what is the distribution factor for the fractional slot winding? The formula is sine sigma by 2. Sk sine sigma upon 2 Sk. Clear? In case of two-phase winding, what is the sigma? Sigma is 90 degree. So it is sine 90 by 2. Sk is 7. Sine 90 degree. 90 degree means 90. 2 into Sk. Sk is 7. So the KD would be 0.9022. So this is the formula that we have to use to find out the distribution factor of a fractional slot winding, in which Sk will be the numerator of slot per phase divided by pole by eliminating the common factor, maximum common factor. Clear? It is called the phase spread. Sigma is basically Q gamma. What is the Q? Sigma is called the Q gamma. Phase belt multiplied by the slot angle. Okay, now I come to the last question of this class. An alternator with synchronous reactance of 0.9 pu is connected to the infinite bus at rated voltage with excitation EMF is adjusted to 1.2 pu. The alternator delivers 0.5 pu output. Neglect all losses, not oil. Neglect all losses. What is the value of armature current? You have to find out the value of armature current. Okay, this is the last question. I am giving the 4-minute time. Synchronous reactance is given. It is connected with the infinite bus bar, means the terminal voltage is equivalent to 1 pu. EF is 1.2 pu. Neglect all the losses. Alternator delivers 0.5 pu output power. Find out the value of IA. The magnitude of armature current would be VT is given, EF is given, XS is given, the power, active power is given, C 0.515. As per Neeraj, C is the correct option. Still you have 1 minute 40 seconds. Only Neeraj solved till now. Hand is giving C is the correct option. What about others? Just find out the value of armature current when Vf is given, Vt is given, power is given. Yes, inverter में important है. Pulse width modulation is the important topic. Even the PWM is the most important topic in inverter. Only 30 seconds remain. See, we know the Vt is given because it is connected with the infinite bus bar. So what is the Vt? Vt magnitude is 1 pu. EF is 1.2 pu. Power is 0.9 pu. And excess is 0.9. Power is 0.5, sorry. So we know P is EF Vt. Excess into sine delta. EF is 0.5, EF is 1.2, Vt is 1, excess is 0.9. So from this you can find out the value of sine delta. Delta you will get 22.02. This is the load angle. That is the angle between E and V. What is the load angle? It is the angle between EF and Vt. Now we are talking about alternator. In alternator, EF always lead the Vt, so the delta is always positive in case of alternator. Clear? See, suppose if you roughly draw this, this is my EF, suppose this is my Vt, and this is EF. EF is leading the Vt. Vt, EF. EF is leading the Vt in case of alternator. So what is this? What is this? What is the formula of alternator? If you neglect the value of Ra, it is given. Neglect all the losses. That means Ra is neglected. That is the Vt plus GIE-axis. If loss is neglected means Ra is neglected. Vt plus GIE-axis. So it is the Vt. So this is basically GIE-axis. This phasor is the GIE-axis because the sum of these two phasor Vt plus GIE-axis is equivalent to the EF phasor. And we know that angle between EF and Vt is equivalent to delta. This is the delta. So if this in this triangle, if you use a trigonometric equation, what is this trigonometric equation? Suppose this is my A, this is my B, and this is C. In a triangle ABC, the BC square is AB square plus AC square minus 2AB BC into cos delta. This is as per the trigonometry. In a triangle, we can use the BC square is the AB square plus AC square minus 2AB BC, and the angle between the AB and BC cos delta. Now, what is the BC? BC is the I axis square. AB is VT square. And what is the VT? VT is 1. So it is a 1 square. AB square, sorry, AC square. This is AC. AB AC, no? AC is EF. EF was 1.2 minus 2, 1 into 1.2 into cos delta. Delta we just find out. It is 22.02. So from this you will get the value of IXS equivalent to 0.463. So from this you can find out the value of IA. It is 0.463 divided by synchronous reactance, which was 0.9. So it is 0.515 pu. Yes, you will get the all PDF in my Telegram channel. See, always remember this formula. This formula is applicable and it is very important formula we use in so many numerical to find out the value of IA. It is applicable for motor as well as generator, because angle between EF and VT is always equivalent to the delta, whether it is a motor or generator. So always remember this formula. It is a very important formula. IX, this is applicable only if we neglect the value of RA. IX square equivalent to VT square plus EF square minus 2 VT EF into cos delta. Clear hai? So this was my last question. You can contact with me through my Telegram ID Ajay Gupta _JPR. All the PDF is available of this class at this Telegram channel. You can also connect me through Instagram. It has the same ID Ajay Gupta _JPR. Through email or through my Facebook, you can connect by using this email ID Ajay Gupta iesgate@gmail.com. Yes, any doubt? So in this way we completed the overall electrical machine, transformer, induction machine, DC machine and the synchronous machine, and I try to cover all problem from all different concept of electrical machine. और हमने उस टॉपिक को भी कवर किया है जो लीस्ट एक्सप्लोर रहते हैं, जिसको हम लोग छोड़ देते हैं. जैसे टुडे आई ट्राई टू कवर हाउ टू फाइंड आउट द इंड्यूस्ड EMF in a single conductor, induced EMF in a coil, then induced EMF in a phase winding. So you must know all these things, where we have to use the pitch factor, where we have to use the distribution factor. I also cover some topic from active power and reactive power, from some efficiency. So this is all about the electrical machine. I think you must have get the enough confidence whenever you go to the GATE exam. Definitely you will solve all the problem of electrical machine. Next subject is not decided. Maybe if it is possible, I can do this the same type of series for the power electronics. Whenever it would happen, I will let you know. Okay, so I'm closing my class here. So good night everybody. Thank you for attending the class. Share the link of this class to other students so that they may also connect with us. I will try my best to start the power system.